Let me share my file here, and I will start the file. Everybody hear my sound or not? So, what is the hydraulic fracturing? In this webinar or workshop, for after some minutes, we will take a break for 5 minutes or some question about the hydraulic fracturing. And again, we'll start with fracturing fluid and Proppant, and again, 5-minute break. And after that, the design procedure for the hydraulic fracturing will start. And at the end of the webinar, I wish that you are happy about the hydraulic fracturing. So I am Peyman Daneshvar from Iran, and I am a instrumentation engineer at Dana Energy Company. And this is my brief story about the Dana Energy Company. It's a big private company in Iran. And as a part of the pledge of the greener future, Dana Energy has made an active investment in solar farm and carbon recovery. So let's start with some outlines that I want the outline to explain about the geomechanics and stress definition, hydraulic fracture definition, geometric model, Proppant and fracturing fluid, and also hydraulic fracturing design procedure. And if we have more time, Nikhil, I want to explain more about the Gopher basic design workflow, just for the showing of the software and data entries. So what is the well simulation? As always, I told before and I tell now, who is a well simulation engineer? Well simulation engineer like a doctor that when a well is got sick, okay, now you are a doctor, give him a medicine, okay? So, for well simulation in a well, our primary goal is to removing the damage and increasing our productivity, okay? And increasing our productivity. So, some of our common jobs and in well simulation that we do is a matrix acidizing, fracture acidizing, and hydraulic fracturing. So in this topic, I want to about the hydraulic fracturing and hydraulic fracturing. This is a very influent simulation formula, or I want to tell you about this is a mother formula in oil industry about the production. Whenever you see this formula, you can see that everything that independent of on the production, you can see that the permeability, thickness, radius of well, radius of penetration, or also a skin factor, and also a viscosity. So in a hydraulic fracturing, what we want to only just increase the wellbore radius or effective well radius. As you can see here, every time in a university or in industry, every time that told us that whenever our skin factor is in negative, the well is in improvement, and in positive, the well need to a stimulation, okay? And whenever is the zero, it starts just in a normal way. And in a sandstone, whenever you do acidized jobs, it will be just near to zero. But in a carbonate, you can minus it to and take it to a negative quantity. Some stimulation technique that you can see in a table just once about the prop fracturing, hydraulic fracturing. You can see that prop hydraulic fracturing job to increase the radius of the well or reduce effective radius of the well. Why? Because in a past slide, if you see that, if you raise this one, the radius of the well, you can give a small logarithm quantity and give you a better production. And another acid fracturing jobs that give you a drainage radius, increase your drainage radius. The prop fracture can be from tens to several hundred meters line, and it usually has a width of some 5 to 35 millimeter, thus increasing the effective wellbore radius. I will talk about all parameters that you see here, but first of all, I want to give you a history about the hydraulic fracturing. Hydraulic fracturing, one of the technique that developed by Halliburton company in 1947, but it didn't have any good result, and now but the technique will improve and develop, and the name established with the Halliburton name in 1949. But hydraulic fracturing is operation. Maybe it's a high-risk job. You do these jobs, but every time you should consider maybe your well is and your result is not good for you. It's a high-risk jobs. High-risk jobs. You cannot consider all parameters together, and you see that now your parameter, all of them good, and now you get a good result. No, nothing more. Hydraulic fracturing is a process of creating a fracture by injection of fluid into a formation at pressure higher than the fracture pressure of the formations. And now for hydraulic fracturing, for now, just a pressure so important for us. In a pressure, okay, now fracture gradient is more important now, is important for us. I will talk about all parameters in some next slides. Enhance the connection between the wellbore and the producing reservoir by creating a conductive path. If you can see in a photo, down the slide, you can see that when a fracture done, you can see that a fracture with some wormhole or with some flow to fluid the well fluid to the wellbore. Okay, but this one, if you comparable the fracture well with unfractured well, you can see that how much the difference between the fractured well and unfractured well. And what a hydraulic fracturing are always good for the low moderate permeability reservoirs, and it's good to, for example, for gas well smaller than a 1 millidarcy, and an oil well is for the 10 millidarcy. Okay, this is a normal range of the job and parameter for the hydraulic fracturing. Hydraulic fracturing. We can do a hydraulic fracturing with non-active fluid. Sometimes a frac acidizing and the hydraulic fracturing will be mistaken together. I want to tell you about that. In acid fracturing, the acid etched, but in a hydraulic fracturing, Proppant keep the fracture open, And in a hydraulic fracturing, you do it in a sandstone. In an acid fracture, you do it in a carbonate formation. And about the differences in fluid losses in acid carbonate, in an acid fracturing, we need to excessive fluid loss. But in a hydraulic fracture, we want to control the fluid loss. Acid fracturing corrosion, because the acid will be a corrosion parameter for us, and another about the cost and anything that you see here. In a carbonate formation, we do matrix or acid fracturing, but in a sandstone, keeping in mind, just for sandstone and also a shale, okay? And also a shale, we can do a hydraulic fracturing. Fracture acidizing involves injection of the acid down the well at a rate faster than the formation can accept and created a natural flow channels. Since the rock will not accept all of the acid pressure buildup, and finally the rock ruptures and the acid injected down the fracture within the carbonate formations. Why we do hydraulic fracturing? We have more object, but sixth one is important for us. Bypass near verbal damage, increase the drainage area, and also increase effective valve radius. Connected with natural fracture, connect with disconnect zone of the formation, connected with thin layer, reduce the sand production and really consolidated formations. So these are our 6 objective parameters that we want to do a hydraulic fracturing jobs. As you can see here, if maybe it's not clear for you, because if you see that here, if you want to find the difference between the hydraulic fracturing, acidizing, and natural fracture, you can see here. If you see that the blue one, you can see that the nature fracture. It's a nature fracture. And if you see a red one, you can see that fracture acidizing. You can find it with the color, with the reaction of the acid with the stone or rock. And another one, yellow one, is the hydraulic fracturing that we can do it. And the past you can see here is some, and also you can find the difference between the frac acidizing with the color. Low permeability sandstone reservoir for hydraulic fracturings, and carbonate for the matrix and the acid fracture. So I started with our geomechanical principle. For example, at first I want to tell you about some in-situ stresses that all stimulation engineer, all engineer that should know about the stresses in the field, because we have 3 more stresses in our local stresses, and in-situ stresses, effective in-situ stresses, and also we should know about the pore pressures, about the fracture gradient, about the breakdown pressure. Now, the in-situ, what is the in-situ stresses? The in-situ stresses affect the hydraulic in local is given at rock and mass at the depths. We have 3 one, vertical or overburden, and 2 horizontal. Vertical and 2 horizontal. That the would qualify with the compressive and the anisotropic and non-homogeneous that we can express about the stresses. And over time, all these stresses will result of the overlaying rock, burial history, pore pressure, temperature, rock properties, diagenesis, tectonics, and viscoelastic relaxation. Okay, these are not always the same and not fixed or constant. Every time when you do a drilling, production, or fracturing, you can alter you can alter or change all these stresses. What is the stress meaning? Forget about the knowledge, forget it. Stress like the pressure. The unit is the same with the pressure. It's about the force that is acting on formation rock at any depth, and we must overcome this force to open the fracture. For most sedimentary basin, yes, we have three principal stresses. Vertical, we show it with a sigma 1, or also always we can use instead of sigma S symbol to show the stresses. Sigma 1 is which equals to weight of the overburden and being the largest. And another one is the two horizontal stresses, a sigma 2, which means that the intermediated stresses, or show it with a sigma capital H, or also SH. Another one is the sigma 3, is shown with the small h, and we can tell we can tell it about it is a minimum stress, a minimum in-situ stresses of the formation. If you can see here, this is the condition of the stresses in a rock, the overburden or vertical, and the sigma at 3, and also sigma 2. As I can show you by lovely Rubik, this is the overburden or vertical. This is the horizontal, one of the horizontal, and this is the minimum horizontal. The vertical one. Now I want to express a little about some these stresses. The vertical maximum stress can usually obtain it from the integration of density lock. Okay, so keep in mind, when we want to talk about the vertical in-situ stresses, how can find it? Okay, with an integration of a density line. Okay, integration of a density line. And if we don't have any data about that, we can find, and we can keep in our mind with a rule of thumb that it's about 1 to 1.1 psi per feet, and it's generally a good approximation for this stress component. As you can see here, it depends on the true depth, depend on the density, and also acceleration due to the gravity. It's as like as our pressure that we know about the pressure formula in our physics, in our guidance, in a higher school. And if you change it and change the parameter, you can see this parameter as sigma v, or vertical. It's about the rho h as a denominator, and 144 as a denominator. And we use this formula always, or sometimes this formula is depend on that if you want the SI parameter or the oil field parameter. Horizontal stresses that I told before is like this one. Yes, this is a vertical, and the horizontal stress is a perpendicular to overburden stresses. So always all stresses will perpendicular together, okay? For the Iranian Amud Baran. Two overburden stresses are normal to each other. So always they should be different, okay? But in an ocean, because we don't have any rigidity, our horizontal stresses will be equal to vertical stresses. So if our formation has a rigidity, okay, now our in-situ stresses will be different. The rule of thumb again, a stress gradient for the minimum stress, minimum horizontal stresses is the point, and the maximum stresses is about the 1.1 to 1.5 psi per feet, and a good approximation for the stress component. As you can see, just for showing you about the direction of the in-situ stresses over buildings in the top, maximum and a minimum, and you can see that the pressure gradient, and important things that you should keep in your mind. Fracture will propagate on the direction of the maximum stress are perpendicular to minimum stresses. So keep in your mind, because we need this one for the choosing the direction of the fracture in hydraulic fracturing. Why we should know about the stresses? Because when we find the stresses, we can find the breakdown pressure, we can find the also fracture directions. Okay. Horizontal stresses. We have two minimum and maximum horizontal stresses. Always they should be different together. Why? Because of the tectonic stresses. Because of the tectonic stresses. I'll show it in a graph, and you can see that what is the difference between the maximum and minimum horizontal stresses. Some tectonic plates is spreading, subduction, and transform. If you can see, the subduction goes down and the spreading together comes up, and another again subduction comes down. So keep it in your mind and think about that. Maximum horizontal stress will be equal to sum of the minimum horizontal stresses and the tectonic stresses. Some of my slides will be showing with some stars. This is just I want that you should know, because it's not a certain rule or anything. In this slide is about a bracket and one equivalent. Give us a formula about the horizontal stresses, minimum horizontal stresses. How we can find it, how we can calculate it. If you can see in a formula, you can find the two important parameters. Okay, one of them is the depth, and another one is the pressure. Which pressure? Pore pressure. Okay, I will explain about the pore pressure in some next slides. So if you can see here, this is just for the Gulf of Mexico region, and also if we can use it for the relaxed areas like the North Sea, because the tectonic plates are there in a relaxed station. Yes. About the pore pressure, we can find it sometimes whenever it's abnormal, and sometimes it's a normal pressure. What is the pore pressure? Pore pressure, you think, is the same with the reservoir pressure or not? Pore pressure is derived from the fluid trapped in a void space of the rocks. The pore fluid carried the total stresses applied to the system, while the matrix carried the rest. When a formation fractures, cracks are created within the rock matrix, a fluid in the wellbore blasts into fractures. The pressure required to create a fracture is temp fracture pressure or breakdown pressure. We know about it, and we should know about the fracture pressure and also about the surface injection pressure. Again, for a pore pressure, as a pressure for density is important for us, and also a depth is important for us. But a normal range for us about the pore pressure is about 0.44 to 0.46. If you can see here, it's about some periodic time in the Passover era. If you see here, pore pressure will decrease when near to our nowadays, okay, because of the maturity of the reservoir, maturity of the rock, and anything that you see for the reservoir parameters. For in-situ stresses, we can find some formula about all of them and some rules. If we are in shallow wells or shallow depths, if you see here, for shallow wells, our horizontal stresses will be bigger or greater than the vertical stresses. But after 500 meters, will be different. So our vertical burden stresses will be greater than the horizontal stresses. You keep it in your mind about this table as you see here. As you see here about the if remember, I told you I will show you about the tectonic stresses between the maximum and minimum horizontal stresses. If you see in a chart or in a photo, you can see that about the differences between the more horizontal and minimum stresses shown with the sigma tectonic. Okay, it means that tectonic stresses. Means that the tectonic stresses, and keep it in your mind again about the shallow depths, and the greater than the shallow depths, which means that about the greater than the 500 meters. It's just an approximate quantity. It's an important parameter or stresses that all should know about this one. It's effective stresses. What is the effective stresses? The overburden stresses or vertical stresses is carried by both the rock grains and the fluid with the pore spaces between the grains. The contact stress between the grains is called effective stresses that we show it and we show it with this sigma prime, okay? And if you always you see that the prime on top of the sigma, you can find the effective stresses that we can, for the vertical stresses, when we want to find the effective stresses, as we show that another parameter that we should consider about that one is a pore pressure. You see that another Biot pore elastic constant approximation is always about, for sand, the sun is normally between this 0.6 to 0.8, but always we should consider about 0.7. Okay, we find the formula about effective and vertical effective stresses, and you can find another formula here about the horizontal minimum horizontal stresses and the maximum horizontal stresses. How we can find the minimum? Okay, sigma sigma h equal with the sigma prim h so with some equal to sum of the sigma prim h and the pore pressure and the constant Biot pore elastic constant. Keep it in your mind. We will solve a solution and we will solve a problem here, and you can understand about this formula as much as you can. Here, just we talk about the stresses. Now we know about the stresses. We know what is vertical, horizontal, minimum and effective fracture will propagated perpendicular to the maximum stresses, and all parameters that you should know about the stresses. Why? Because all of them important for us. And now about geomechanical parameter definition: strain, stress refined, stress, Poisson ratio, Rhine modulus, shear modulus, bulk volume modulus, and bioelastic and fracture gradient. What is the strain? This is like this one. I want to push it. Okay, now I want to pull it. This is the strain. Okay, this is the full strain. But what is the meaning of strain in a knowledge? Elongation at break, also in knowledge, also in fracture strain, is the ratio between the changeless and initial length after breakage. If you see that our nominator is the DL, is the differential of the length, the difference of the length, and but our denominator is L because the initial length. So what is the strain? You can find it with this formula. Another, what is the Poisson ratio? Poisson ratio is a ratio of transverse contraction or expansion strain or lateral strain to longitudinal extension strain, linear strain in the direction of a stretching force. If you see here in the both picture, you can see this is like this. Let me show you again with my Rubik. This one, we push lateral strain, longitudinal strain. This is the ratio between these two types, okay? When you do these types, you can find the Poisson ratio. A general Poisson ratio between the 0.2 to 0.3 reservoir for the reservoir rocks. How we can find the Poisson ratio? We can find the Poisson ratio is determined from the core samples, and also when, first of all, you should find the Young modulus. After Young modulus, you can find it with the Poisson ratio. If you didn't check any Poisson ratio, you can find it with the sonic likes. If although this is less reliable, you can find it how we can calculate the Poisson ratio with the sonic likes. You can see that it depends on the compressional wave traveling time and the shear wave traveling time. Here a table that you can find it about the sandstone, dolomite, and limestone. It's a ratio between the shear wave traveling time with the compressional wave traveling time, and in the next picture or table, you can find that the Poisson ratio quantity for each type of the sand in a dense, coarse, or fine, or sealed, clay, unsaturated, unsaturated, some of them in here. Where we use this parameter when we want to do or to solving the problem. What is the Young modulus? Young modulus is the slope of linear part of the stress strain curve for a material under tension or compression for a ductile material. The Young modulus stresses elastic stiffness, or how much energy it needs for us to deform the material. Okay, the fracture, it is important parameter for the hydraulic fracturing because we can find it with this one about the fracture dimension and also pumping schedule. A larger value of a Young modulus will give us a narrower fracture and consequently a smaller Proppant loading in the creating schedule. So as you can see here, the Young modulus equal with the ratio between the stresses to strain. Here you can identify about the Young modulus. Okay, Young modulus, how much energy it takes to deform a rock. Okay, if you see here, a tilt to yield length is a modulus of resiliences that do as a Hooke's law. And from the yielding stress into fracture, it's a modulus of the toughness. What is the toughness? I will talk it later. Yes, because now I want to push it, or pull it, okay? But now it's separated. Now deforming. Now the fracture will happen. Again, I want to show you that I told before, for the hard rock, for the high Young modulus, we have tends to transmit the stresses, high pump pressure, and then our fracture geometry will be long and narrow, okay? But if you can see in a picture, for a soft rock, tends to deform, challenges for pond embedment, and fracture geometry short and wide. Although, of course, this is not a equal quantity of the high Young modulus and also a soft Young modulus. This is just an approximate quantity. Another one that when we want to find the Young modulus, we can use the Brinell hardness number. What is the Brinell hardness number? The Brinell hardness number, which is measure of the rock's hardness, is used to calculate pond embedment in the fracture. One, if no value for Young's modulus is available, the BHN will be used to calculate the Young modulus. So it's an alternative methods to calculate of Young's modulus. If you want to do, if you want to find the Young modulus with the sonic light, you can find it with this formula. It's about the acoustic compressional weight or traveling time, and also depend on density and also Poisson ratio and the reservoir porosity. This is some quantity for the Poisson ratio and Young modulus for some rock type of formation type. For the soft sandstone, for a medium sandstone, also hard sandstone, limestone, coal, and shale. If you can see here, it's show it with the megapascal because of the SI unit, but sometimes we maybe confirmed with the PSI, with the mega PSI. What is the shear modulus? Shear modulus, also known as modulus of rigidity, is the measure of the rigidity of the body given by the ratio of the shear stress to shear strain. It is often showed by G or S or also mu. But it's a common that we use a G for the shear modulus. If you remember that the Young modulus showed with the E and the shear modulus with about the G. And shear modulus is a ratio about the shear stress and shear strain. Keep in your mind about this formula because we need this formula for the solving our problem. Another parameter is bulk modulus that we show it with a K or B symbol. Bulk modulus is a measure of the ability of substance with a slight change in volume under compression or offside. Again with my rubric, this is the bulk modulus. This is for the ratio between the differential pressure and in a change with a standing, in a change it in volume. It is equal to quotient of the applied pressure divided to the relative deformations. These are formula that you can find it for yourself in solving problem because you should know all parameter. One sense that everybody tell, please on time, if you remember or if you comfort with a new formula, please use this formula in your Excel file and using your own software for yourself. Because always you cannot remind all parameter and formula, keep it in your mind. Please make a own Excel file for all formula that you comfort or your see in your schedule of the time, schedule of your work. This is just not advice, just a sentence that I want to tell you, do it for yourself. What is the Biot for elastic constant coefficient? The Biot coefficient is a parameter that is counted in the theory of classical elasticity dealing with the mechanics of fluid saturated metal structures. Always, as I told before, the range of the Biot for elastic is about 0.6 to 0.8, with supposing that our right porosity is about 20%. And another formula that is not accurate, but sometimes some lab engineer do it with a formula that a grid small and a schematon gave us. It's about the alpha. It's equal with difference between the 1-to ratio of the bulk volume of the formation and the bulk volume of the matrix. What is the fracture gradient? One of our important parameters that we want to know about the surface injection pressure and also about the breakdown pressure. Fracture gradient is that defines the required pressure to apply break formation at a specific depth and create a fracture. Guys, unfortunately, all time we comfort with some fracture gradient of the field that give us another fracture gradient near to this field for next field near to our field. And he or she asks us to give them a best program to him or her. Why? How we can? Whenever you give us the inaccurate, the fracture gradient, because it's important parameter in a hydraulic fracturing, forget about the fracture fluid and proppant, is a fracture initiation pressure. or fracture, it's about the breakdown pressure. And how we can find the fracture gradient in a field? We can do it, and we can find it with three operations. One of them is the stir break test. One of them is a Mini-frac test, and another one is for a leak-off test or formation integrity test. Yeah. Sorry for cementing operator assistant all time in a field, because all time that when anybody wants to company-man or anybody wants to find the fracture gradient or find the or wants to do a FIT test, they should every time go upside to the unit and take the test. These are schematic jobs that some parameter it's important for us and some equipment should we have. If you see here, we need a fracture fluid storage, we need a pump rack, we need a blender, we need the discharge tanks, we need the pump racks, we need the manifold, and also we need some parameters, some sensor pressure sensors, we need the flow meter, we need the computer unit or computer van, because if we want to because we should always check all parameters during the jobs. What is the hydraulic fracturing procedure? Hydraulic fracturing procedure divided in two stages: pad stages or slurry stages. In a field, we can tell about the slurry stages equal with the PLF step, the PLF stages. What is the pad stage? Pad stage is just a fluid, fracturing fluid without proppant or a neat fluid. What is the slurry stages? The slurry stages is a fracture fluid with the proppant mixing, and now we give you a slurry stages. So are two divided, we divided in two stages, one of them pad stages and another slurry. That we can tell him, we can tell it PLF stages. How Suchitra, I think, let me explain this sliders, and after I explain it till to fracturing fluid, I will give you some minute for break time, and you can ask your question. Just write your sliders number and ask your question about that slides. Thank you. Operation procedure. For example, a fracture. First of all, if you see that for the pad stages, with the pad stage, our proppant tank closed, because just we want to inject the fracturing fluid. We inject the fluid to create the fracture. And because of the fracture tends to close, and we should now put a proppant with the fracture fluid and mix it together, and now pumping our slurry stages, because fill fracture with the same proppant and inject frac and the proppant mixture. If you see that in this here, three valves will open: proppant, fracture fluid, and injection and pumping valve after the pump track will open to the well. If we can see that the empty places will be filled with the Proppant. But another picture that I put it here for acid fracturing, acid etched the fracture as like as these pictures. After the job finish, we close all parameter and we see the unit to pressure curve and another parameter. This is the procedure. Well is ready. We start pumping. Which pumping? Pad stages. We pad stages as like as the Slickwater linear shell, because we want to initiate fraction, reduce the friction, cool down the formations, or we want to introduce the formation to hydraulic fracturing. Now you are ready for the hydraulic fracturing, okay? And another one, fracture will go inside, go inside, enhance the fracture dimension. Fracture continues growing and propagating. After that, the fracture tends to close. Now we should use our cross-linking gel or slurry stages that the mixing with the Proppant stage from the low to high Proppant concentration, because every time in hydraulic fracturing, when we want to increase the concentration of the Proppant in the shell, we should step and gradually increase the Proppant concentration, because the screen out problem. Proppant screen out problem. So the slurry go inside the well, the slurry go inject more and more and more to fill fracture. After that, why? Because we want to displace Proppant from the wellbore to fracture, and displace to keep fracture conductivity up and at the perforation faces. And after we do a flush jobs, we shut in the well and allow the fracture close due to gel breaks and fluid leak off. And breaker, I will talk about breaker and you see here, breaker can break in a formation to clean the residue of the inner well. In a last stages, we clean up the well because we recover the polymer to avoid formation damage due to unbroken shell. Why we use broken and break the formation damages in a check and clean up the wellbore. This is just a sample of the operation history. We pumping with the pad stages, with the slurry stages, flushes, and shutting. You can find the difference between the pressure and the rate of the pumping and all. This is the hydraulic fracturing growth. It means that how it show this picture will show us about the how the fracture initiation will occur here. At first, we inject fluid. The fracture initiation as a pumping of fluid is fracture to treatment. The fracture will be bigger and bigger, and the fracture will be filled of the Proppant. In the next stage, fracture propagation with fluid other things that Nikhil, I will the question box will be in an outbreak. Here again, proppant advanced further into the fracture and may reach the tip of the hydraulic fracture as fluid continues to leak into permeable formations. Pumping of fluid mixture is stopped and continues to leak away into preparation. Formation closed on proppant and a conductive path remains in the reservoir. If you see here, this is the graph of the hydraulic fracturing and also a minor frac jobs. This is the number 1 for initiation pressure, 2 for propagations, breakdown pressures, and you can find it for the end of injections, and again you can find it for the fracture closure pressure. Okay, fracture closure pressure, it's equal with the minimum horizontal stress. Please keep it in your mind. Every time the fracture closure pressure will be equal with the minimum horizontal stresses, and the down and lower one is the pore pressure, formation pore pressure. What is the fracture initiation pressure? The pressure needed to start the fracture propagation from the perforations. So what is the fracture initiation? The pressure needed to start the fracture propagation from the perforations. And fracture propagation pressures. What is the fracture propagation? It's a sum of the minimum rock effective stresses with the pore pressures and fracture toughness. What is the toughness? I told before, and I will explain in some next slides. And always fracture initiation will be greater than the fracture propagation. Why? Because of the tensile stresses present around the borehole. Keep in your mind. Why? Because of the tensile stresses present around the borehole. Fracture toughness. What is the fracture toughness? Describe the resistance of the brittle material to the propagation of the flow for urania NACS under and applied stresses, and it assumed that the longer flow, the lower the stress needed to cause fractures. For toughness, we have 2 parameters: critical stress intensity factor, and another one is the stress intensity factor. The stress intensity factor describes the stress state near the tip of the fracture, as like here. If you see here, tip of the fracture, we do a fracture, tip of the fracture, stress near tip of the fractures. So when our stress intensity factor, is smaller than our critical stress intensity factor, our fracture does not propagate. But if our pressure, our stress intensity factor will be equal or greater than the critical density factor, or our fracture toughness, our fracture propagated will be effect. What is the net pressure? One of our important parameters that always we comfort about in designing, it's a net pressure. When we want to solving a problem, you can see that how the net pressure is important for us. The net pressure is the pressure that a difference between the pressure inside the fracture and a closure pressure. closure pressure, if you keep it, if you remember, closure pressure is equal with the minimum horizontal stresses. So how we can find it? With this formula, net pressure equal with the pressure inside the fracture minus with the minimum horizontal stresses. The fracture fluid pressure must exceed the minimum in-situ stresses in order to generate fracture widths. Indeed, the fracture width is proportional to the pressure in excess of minimum horizontal in-situ stresses. This excess pressure is called a net pressure. Two main processes contribute in net pressure: fluid friction and another fracture propagation. Fluid friction pressure is required to squeeze the fracture fluid through the fracture, and another one of pressure is required to generate new fracture area. Typically ranges, net pressure ranges from the 1 to 10 megapascal. Okay, this is a small problem here that we want to know how the fracture toughness will help us. The problem: calculate the maximum width and stress intensity of a fracture with a half length 10 meter and pressurize 20.5 megapascal, immersed with the elastic medium Young modulus 1 gigapascal and a Poisson ratio and subjected to so far. Okay, sometimes in a formula, instead of Young modulus, we use a parameter that we tell that the plane strain Young modulus. That we can show it with this formula, a Young modulus as a nominator and a Poisson rate differential Poisson ratio in a denominator. So when you comfort with the E-prime, it means that a plane strain Young modulus. Okay, it means that a plane strain Young modulus. So what is our pressure, net pressure? You see that we have the pressure. Okay. Another, what is our minimum horizontal stresses? You can find it here. And another one, what is the maximum width? Maximum width. This formula, this is just not depend on any geometric model or anything. This is just for showing you about the fracture toughness, nothing more. Just an example for you. It's you can find this formula for yourself. Just if you see that with the replace the quantity together in here, you can find the fracture toughness, and after that, when you find the fracture toughness, you can find the width of the fracture. So first of all, we should find the net pressure. Okay. Another one, we should find the fracture width. After fracture width and with the strain Young modulus, we can find the fracture toughness. And it's important for us that in a normal, our width would be twice of the when we are in a center, our pressure in the center and decreasing linearly to 0, twice, twofold. A pressure breakdown what is our breakdown pressure? Mr. Terzaghi gave us the formula for upper limit and lower limit. Our lower and upper limit will be defined by the minimum horizontal stresses and the maximum horizontal stresses, pore pressure, and the tensile stresses. And for lower limited is just for about the, because without of the tensile stress and pore pressure, it depends of the minimum and the horizontal stresses. So we always, when we want to find the breakdown pressure, we use a Terzaghi breakdown pressure. It's as you can see here. And what is the stylus and what is the tensile stresses? The tensile stresses of the formation is used to calculate the fracture initiation pressure and may be obtained from core samples. Keep it in mind about the Terzaghi breakdown pressure. The example here, a sandstone at the depth of the 10,000 foot, okay, now we have a depth. A Poisson ratio, okay, we have a Poisson ratio. Another one, a poroelastic constant we have. The average density of overburden, okay, 165 PCF. The pore pressure gradient in a sandstone give us, and assuming a tectonic stresses or tectonic stresses is 2000 psi and tensile stresses of a sandstone is 1000 psi. Predict the breakdown pressure for the sandstone. First of all, we should find the vertical stresses or overburden stresses. After that, we can find the pore pressure. And another one, we should find the effective vertical stresses. We should find the effective vertical stresses. When we find the effective vertical stresses, with the formula, as you can see here, we should find the effective minimum horizontal stresses. After minimum horizontal stresses, we should find the maximum horizontal stresses, and with the Terzaghi breakdown pressure, we can find out our breakdown pressure will be 6,600 psi. So now we find why in-situ stresses is important for us. Why? Because we can find the breakdown pressure. Why pore pressure is important for us? Because we can find the breakdown pressure. We should know all of them and all formula, and keep it your mind about this formula in Excel file and do it with your Excel file, because every time you cannot keep it your mind all formula. How we can find the fracture pressure data? In a field or prior to hydraulic fracturing jobs, we should do a Mini-frac jobs. What is the Mini-frac jobs? It's a simulate like a hydraulic fracturing jobs that I will explain how we can interpret it and how we can do it in a jobs. Depend on the volume of the pumping. Depend on the volume of pumping, it will be different. Smaller than the 5 cubic meter is a microfrac, and another one is Mini-frac, and it's smaller than the 50 cubic meter. If you see here, this is a graph or this is a chart that we can find the how we can find the fracture initiation pressure. This graph will be showing more and more, because this is an important part and this is important chart that we should know, and we should know about all parameter here, pressure and anything, and you can find it. about the fracture initiation pressure, fracture propagation pressure, fracture closure pressure, and also about the minimum horizontal stress. If you see here, arrangement for Mini-frac treatment, just we inject the fluid inside the fracture and observe it with our monitoring. We are monitoring in one unit. This is the bottom hole pressure brings, this is for explaining about the fracture initiation pressure, because when we injected the bottom hole, inject the fluid, our bottom hole pressure begins to rise until to fracture initiation pressure. After that, it drops rapidly to fracture propagation, and the pump will be stopped and pressure rapidly to the instantaneous shutting pressure. And again, the fracture is still open, and the pressure drops until the fracture closure pressure equal to minimum horizontal stresses. And a second cycle would normally occur at a lower value, the fracture initiation pressure. This is a quantity. Now I want to tell you about the fracture direction with stresses. As the growth of a vertical overburden in almost, I told you before that, the fracture gradient, the gradient of the stresses for the vertical stresses is about the 1.0 to 1.50. Approximately until 2,000 feet, or I told before 500 meters approximate quantity, because just this is for some references, because some region will be different about this depths of the depths of and the stresses will be changes. So we want to know about which stresses will be greater and which stresses will control the fracture directions. So if you see that fracture is always propagated perpendicular to direction of the minimum stresses in the formations. So if you see here, when our vertical stresses bigger than the horizontal stresses, a fracture will be vertical fracture. If our vertical stresses will be smaller than the horizontal stresses, our fracture will be horizontal. So the in-situ stresses will control the direction of this direction of the fracture. When our vertical stresses bigger, our fracture will be vertical. When our vertical stress is smaller, our fracture will be horizontal. And again, these sentences, fracture is always propagated perpendicular to direction of the minimum stress in the formations, but parallel with the maximum stresses. The fracture orientation, vertical or horizontal, and the azimuth of the fracture plane, vertical height of growth and containment, surface rating pressure, proppant crushing, and embedment. Fracture are generally planar and oriented perpendicular to minimum in-situ stresses, minimum, perpendicular to minimum, and parallel to maximum. Fracture orientation for the drilling, for horizontal wells, if we drill perpendicular to minimum horizontal stresses, the created fracture will longitudinal. If we see that here, photo, that you can see that the parallel with the maximum, but will be perpendicular to minimum. And again, if the horizontal is drilled parallel to minimum horizontal stresses, the created fractures are expected to perpendicular to the horizontal well, and transverse fractures will be created. Again, for the deviational wells, as the rule will be the same for horizontal wells and deviated wells. Intermediate direction relative to direction of the situ horizontal stresses, non-planar fracture geometry may be created near the well, or maybe it has some angle between the maximum and minimum stresses. You can see here, for keeping your mind, for vertical borehole, if our vertical stresses bigger than the two horizontal stresses, our fracture will be the same. And 6 probability here, you can see all of them. Please check it for yourself, because all the time you should repeat this sentence for yourself, that a fracture generally planar or oriented perpendicular to the minimum in situ stresses, but parallel with the maximum or vertical stresses. One of our important parameters is a fracture propagation geometry model. With the fracture geometry model include width, length, and the height of the fracture, and the information is necessary in simulation design. We have 3 common type of radial, KGD, and PKM model. Now, all software that included in a market uses some of this model, some of this basic fracturing propagation geometric model. But for radial model, and we can find it some formula, because this formula can help us that find the width of the fracture. For the radial model, that is adequate for the frac packing in 6 sandstone. If you can see that, we can find the width of the fracture or average width of the fracture with this formula. And this formula is important for us, because when we want to simulate the frac packing in a 6 sandstone, the radial model is okay for us. And another model is a KGD model. In a KGD and PKN model, all time the height of the fracture will be constant. This is assuming that all time the fracture height is constant. And in a KGD model, the shape will be rectangular, but in a PKN model, elliptical or novel. The fracture, but in here, in a KGD model, our height of the fracture will be bigger than the fracture length. One of the important formula that you should know about the KGD model, a difference between the KGD model and the PKM model, it's about the volume of the fracture and about the fracture area. Because if you see this formula for a PKM model, will be different. A KGD model is all can we use it for open hole stresses, not anything for the production point of the view, and we can use it for the short fracture in a 6 sandstone and the KGD model. You can see elliptical cross shapes on the top and a rectangular cross section here. This is the assume that all time that you should know about that the fracture height will be will be greater than the fracture half length. A PKM model has an elliptical shape at the wellbore. You can see here the elliptical shape of the wellbore, and the fracture propagation decreases as the fracture grows longer. Please find that this formula that we want this average width that give us the quantity in inches, then we should once and keep it your mind or your Excel file, because it's difficult to keep it for keeping your mind, because the line formula, and just you should know about that this formula is okay for the PKM model, and gamma in here just a difference between the PKN and the KGD, because the gamma is the value that is a value that the fracture shape factor and approximately to 0.75. In PKM model, I told before, our fracture volume and the fracture area formula will be different for us, and you should be consider all time about these two formula. PKM model, it's good for to simulate a line fracture to be created in a sandstone tightly bonded by a strong overlaying and underlaying shape, and the PKM are more appropriated. For the PKM model, just a Newton fluid is only considered. One of these two, these are some formula that depend on the time. This formula give us the formula that the software used this formula to give us the parameter in each time. So you can find the fracture half-length for the PKM model, for the maximum width, for the net pressure and the volume of the fracture, and that's why for the fracture half-length for for the KGD, and the maximum width at the wellbore and the net pressure at the wellbore. How? Because so that we should keep it in mind. How software use the simple formula for the simulation? It cannot, because you should consider about the time. It should consider about the time that wants to simulate the fracture, simulate the length, simulate the width, and all parameter. This is just for yourself. This is for the some slides we start. It's a questions that we can find it with the time, how was the fracture width, how is the maximum width or the net pressure and the fracture tubing. It's important for us that every time just when we want to calculate the volume, we calculate one wing, but it's or B wing, because we should know about that this is one part of the fracture. We should calculate for two-fold of or twice of the volume. Hydraulic fracture computering module. We have 4 types of the computering module: 2-dimension, PCD 3-dimension, planar 3-dimensional, and fully 3-dimensional. For the 2D models, we can use the PK and KGD model, and the fracture height be input, and so the length and the width we calculate the fluid volume as fluid characteristic. It's a simplistic, but and now we can, when we want to calculate the width and other things, we do it with this parameter. Another one is PCD 3-dimensional PCD and that develop from the PKM model by removing requirement of constant fracture height. As you can see here in PCD 3D, we can calculate pressure drop along the fracture length, calculate the width and equilibrium height at each segment, may have Proppant transport model run security with geometry. And another one, planar 3-dimensional or PL3D, is now for one of the famous software that we use in a market is a Gopher, and that depend on the PL3D planar 2-dimensional flow fracture, power low flows, and linear fracture mechanics for fracture propagations. And the advantage of the PL3D simulation is ability to model the pressure drop laterally within the fractures. And another one is fully 3-dimensional. In a market, some company wants to find a software with this type of the model, but it, because we don't have all parameter, and it's not okay. It's not okay. Absolutely, simulation is not operational. Just for the research is okay. Various fracture design programs: Shell-frac, Gopher, Frac-Brom, MF-frac or Trough-frac, and for Schlumberger frac rate. And we can find here the fracture flow regimes model. We can 4 types of the flow regimes. Regimes. Initially, flow is only inside the fracture. Linear flow pressure front extend both linearly align the fracture and linearly into the reservoir near the fractures. A formation and a flow linearly out from the fracture into a reservoir, and another one is a fracture radial flow. Fracture conductivity, one of the important parameters that in a fracture that in a hydraulic fracture is important for us. But because what is the fracture conductivity? We do a fracture, okay? This fracture, how this fracture can help us? If this fracture can transfer the fluid from the reservoir to this fracture and fracture to wellbore is okay. This is a good conductivity. What is the fracture conductivity? Is a relation between the receiving fluid from the formation and transporting the received fluid into the wellbore. Okay, what is the receiving fluid depends on the fracture dimension, height, and the length, and transporting the received fluid to the wellbore depends on the fracture permeability. As you can see in the picture, you can find it what is the important parameter for the receiving fluid and transporting fluid and receive the fluid to the wellbore. This is the formula that we can find the fracture conductive. This is important for us because when we find this one, we can find the SF or skin factor for fracturing. After the skin factor, we can find the fall-off increase or ratio of increase and how is the improvement of the productions. As you can see here, the fall-off increase as the fall-off increase will be the ratio between the productivity of fracture wells and the productivity of non-fracture wells. If you see that, it depends on the wellbore radius and drainage radius, and also a scheme factor. A scheme factor that in the next slide I will show another formula that we can find it for the fall-off increase, this one. And in the next slides, I want to do and show that how is the conduct, how we can find a conduct, how we can find a scheme factor with the conductivity, fracture conductivity. If our fracture conductivity will be greater than the 100, we can use this formula to find a scheme factor and put it our fall-off increase. And another one, if our our fracture conductivity is smaller than 1, we can find this formula here, and you can find it. But if it's between 1 and 200, we should find it with the Single-Lay and Samanigo curve. We should find the SF plus ln XFRW. We should find this parameter, and after we find this one, we should find the SF, and we again put SF in our fall-off increase. Our optimum FCD or fracture conductivity is 10 to 30. As you can see, they are optimal. This is a fall-off in another fall-off increase that's used in a software. It's about the distance in fracture and directions. This is just for the more informations. What is a Mini-frac test? When we want to gather a pressure, we should do some pressure, and we should do some tests as a Mini-frac test. Or we call that what is a Mini-frac test? We should do it to establish or find the FCP or fracture closure pressure, and to find the overpressure, to find the fluid loss coefficient, and also about the minimum horizontal stresses and all parameters. Now, this is the Mini-frac test procedure, and we can find it at first on time. When you started for operation times, when you want to do a Mini-frac test jobs procedure, when you do it, you should shut in immediately and monitor pressure decline. Okay, for the step 1, this is for fracture initiation. Okay, yes. We do it, we pumping with a base shell or pad slurry with a pad. And another one, again, you check that now the fracture is reopening or optional, zone pumping at a constant rate, because you cannot increase the rate gradually, because you should have a constant rate in a Mini-frac test procedure. And again, for the step down test, pump while decrease the pump rate in a 5 to 10 1-minute step for the maximum rate, depend on in a step 1 or 2 0. You can see this curve for the Mini-frac test, and always you can find it. Again, propagation test, switch over to cross-linked gel and displace the tubing contact to cross-linked gel at a rate corresponding to pressure approximately 2000 psi below the maximum allowable pressure. Step 5, a true Mini-frac test pump at a rate corresponding to a pressure approximately to 2000 psi, again below the maximum allowable pressure. Plus, keep the rate constant after the cross-linked gel has reached the perforation. And for the Step 6, a true Mini-frac is repeat, because if necessary, if the available is a problem, we should do it again. And what is the interpretation? We can find that bit for the first one, fracture initiation. For the step 2, we can find a test on fracture inhibition and propagation pressure. We can find the propagation pressure. And a step down test, it generally not carried to more precisely determine the fracture closure, but it may propose to qualitatively analyze the presence of the natural fracture and trace bottom hole friction problems. And for the step 4, the propagation test may be used to get in an impression of the fracture propagation pressure changes. It also serves to calculate the fracture over pressure and leak of behavior. Leak of behavior, one of the important things that we should know about the parameter is a leak of point, a leak of or fluid loss. True Mini-frac tests, the true Mini-frac tests are used to confirm estimates of in-situ stresses, fracture over pressure, and fluid loss coefficients. This allows on-site revision of treatment design. This is a Mini-frac sample result. You can find it in perforation interval, mid perforation, bottom hole pressure, fracture gradient, closure pressure. This gives us to a simulation engineer or frac engineer, and with this data, the frac engineer will calculate some parameter depending on the pressure. So, sorry for delaying time, and now recording can be stopped, and we take a break for 5. So now we talk about the in-situ stresses. We talked about the fracturing geometric model. And also about the fracture conductivity, fracture toughness, geomechanical parameter, about the Young modulus, and some parameter. I think that I think that it was useful for you. Now just I want to talk about the fracturing fluid. The fracture fluid is a critical component of the hydraulic fracturing treatment. Some purpose of the fracturing fluid basically is transmit the pressure from surface to the well to initiate the fracture. For the first step, hydraulically extend or propagate the fracture into the formation, and also transport or distribute the proppant along the fracture, and also in acid fracturing to create uneven edge flow channels. If you can see here, this is a chart that maybe you can just statistical for the showing you about some percent of that some percent of the fracturing fluid that used normally in a word for the Slickwater, Pore, Core, VES, band, linear gel non-aqueous, while zirconium derivative Core. Fracture fluid should have some properties. The friction losses in tubular should be small to keep the horsepower requirement as low as possible. The fluid loss to the formation should be low as possible. They should have an optimum carrying capacity to transport and propping agent, optimum viscosity to create a maximum fracture penetration into the drainage of the air and the drainage of the well in relation to an adequate width of the placing of the proppant. After breaking, this should be a residual free. It means that a small residue, because the formation damage will be decreased. prevent, again, compatible with the reservoir fluids and reservoir rocks institute temperature and pressure. And about the environmental hazardness and also personal hazardness, about the prices, and about the volume that is readily in around will be in around us. We have some type of the fracture fluid, water-based, oil-based, multi-phases fracture fluid, and liquid CO2 fracture fluid. Now, this always we hear about the oil-based and a water-based, oil-based and a water-based. It's some benefit and some disadvantages. The advantages of the oil base is a low damaging to clays, low interfacial tension, and disadvantages: expensive, difficult to handle, not environmentally friendly. For water base, it's a safe, available, economical, but damaging to the clays, and we should use some additive to control the clay. Now for water base, so why we choose a water base? Because of the low cost, high performance, but ease of the handling, and also be readily near to us every time, and we can use it. And some problem and one of the most important problem that every time will be comfort with the water-based fraction fluid is the formation damage of water-sensitive zone and pack damage caused by unbroken polymer and additive, because the breaker doesn't do its jobs. Water-based fracturing fluid, which are polymer-free, can be prepared using viscoelastic surfactant. Viscoelastic surfactant in acidizing, we use it, but another time when we want to break the viscoelastic surfactant, we can put some mutual solvent to break it. And when the surfactant is added to water, the Modulus associated in the structure called micellus. Polymer are the high molecular weight molecules, and are water soluble, and also can viscosify solution capable with suspending proppant. One of the first proppant they used to viscosify water for fracturing applications was guar gum. Guar gum is natural branched chain polysaccharide polymer. Guar is good, but because of it contains 5 to 10% soluble residue upon breaking, we use some derivative cellulose or derivative as guar that will help us for the less residue, as like as the hydroxyl guar, HPG, and carboxymethyl hydroxypropyl guar, or CMHPG, are basically chemically pure form of the natural guar gums, and the viscosity developed are similar of the guar because of derivative was just hydrated faster than the at lower temperature, give less residue, about 1%, but the guar give us about a 5 to 10% residue and have a high temperature stability here. And another one is for the cellulose derivative, as like as the HEC, hydroxymethyl cellulose, and carboxymethyl hydroxyl cellulose. These are a natural strain polymer. You can see that about the liner polymer, and the crosslink polymer. They provide a good reduction in friction pressure, and they don't degrade to temperature up to 200 centigrade. And the cellulose are often very clean, low residue. Okay, it's good for us because one of the more important parameter for the fluid is low residue. It's a low residue fluid. Another one is crosslinkers. The viscosity of liner gels can be drastically increased by cross-linking polymer moleculars in the solution, because cross-link, as it shows in name, cross-links. It means that the polymer comes together, across together, and will be a viscosified gel, increasing viscosity about 5 to 100 fold in the range of shear rates. We can use some element of like a boron, like titanium, antimony, aluminum, and zirconium to cross-linking metal, and also prepare fluid for preparing the this for guar gum or guar derivative are commonly used to viscosify the low viscose fluid. Here, if you want to keep in your mind, because every time we use this one only, a cross-link HPG system can be pumped into a deep hot reservoirs. Severe shear degradation occurs when the fluid cross-linked at surface and then pumped at the high rates down the tubulars. Here we can see a table about some cross-linkers with a boron, with a zirconium, with a titanium, and you can see that what is the gelling agent is, and what is the range of this fracturing fluid, and also the operational temperature that depend on this parameter. We choose them for the fracturing fluid. As you can see here, is Slickwater with a cross-link shell. The photo or the picture you can see here, like a cross-link shell and a critical entanglement concentration. It means that after dehydration in the fracture, this dehydration in the fracture should be not remain in the fracture, because it will be a residue and it's not good for the formation. What is the Slickwater? Slickwater is a combination of water, chemicals, and a sand that inserted to wet, reduced friction pressure, and created a fracture. Crosslinkers, another famous crosslink is a break in the forming of boric acid, and the optimum borate crosslinkers efficiency at pH about 10.5, and also borate cross-linked fluid can be applied across a wide range of durating conditions and are resistant to shear degradations. And here we can see that there's some characteristics of HPG cross-linked that we use it for the deep. If you see that, we use a crossing HPG system can be pumped into a deep hot reservoirs because of severe shear degradations. And this is the hanging performance of comparison for the different cross-linking based on the amount and the type of the polymer gel. You can see that how is the jelly form of the cross-linkers and how is the hanging performance. Another one about the oil-based fluids. For the oil-based that I told before, oil-based fluid is okay for the formations that we have a clay mineral more. But when we use a water-based fluid, we can use some additive like as a KCl to control the clay controlling for now. But the oil-based fluid, it has some problem for the expensive, for the expensive, and it's not good for environmental. And I told before, it advantageous in certain situations to avoid the formation damage in water-sensitive oil-producing formations. And a crude oil is relatively cheap and compatible with formation fluid because for the oil very gas well, but usually requires the fluidized additive and friction reducer, and it has limited proppant carrying capacity. It's important for us. Proppant carrying capacity is important for us. And another one is a multi-phase fracturing fluid. Is for the emulsion and a foams emulsion is like a mixing oil and water together. Foams means that creating or adding gas to water or oil-based fluid. For example, for the emulsion is dispersion of two immiscible phases such as oil in water or water in oil stabilizes with surfactant. Remember, surfactant will be included in emulsions fracturing fluid. The emulsion-based fracture are viscous solution and good transport properties. The higher percentage of internal phase, the more resistant there is droplet movement, resulting in higher viscosity. The most common, this is important, keep it in your mind, the most common emulsion fluid is polyemulsion that 67% hydrocarbon internal phase and 33% viscosity footprint external phase with an emulsifying surfactant. Again, surfactant will be in there. And the polymer concentration using in general is 20 to 40 pounds per gallon. And so fluid contains only 1/6 to 1/3 as much as polymer. Disadvantage of this high friction pressure and high fluid cost and polyemulsion are seen significantly is as the temperature increases, which limits their use in a hot wells. So we cannot use emulsion in a deep hot reservoirs. What is the foam? Add water or oil means the foams. Foam generally contain 60-80 volume of nitrogen and 40 to 20% of the volume of water with surfactant. Always surfactant will be there to stabilize the emulsion and sometimes with the gelling agent, fluid loss control agent. Their application is attractive in shallow, low permeability gas well zones and containing in a zone that containing water sensitive clays. So shallow, low permeability gas well and a zone containing water sensitive clays. So what is the description of the foam quality? That's about the ratio of the gas volume to foam volume. So for example, this is a one reference. This is not a rule, but sometimes we sometimes we can tell about this quantity about the foam quality. If the foam quality between the 52 to 95 is considered for foam, but it's for the above the 95% is like a mist, and below the 52%, according to Mitchell, a stable foam does not exist but there are no bubble interactions. So again, the important parameter that we want to use the foam fracturings is we can use it in a shallow wells, in a low permeability gas well, and in a zone containing water sensitive place. Foam also has advantage in that it places the minimum amount of fluid of the formations. Another one is for the liquid CO2. It has a history. It has been patented. Process was introduced in 1981, and nowadays do in Canada, in the USA, and Hungary. And the CO2 has some benefit that eliminating formation damages, rapid cleanup with no residual left with the Proppant bag. It's so important for us because give us a good permeability between the Proppant added directly to liquid in a specially developed blender. For the fracturing with the liquid CO2, we should have some special equipment, okay? We should have special equipment. Conventional fluid rely on viscosity to transport proppant into the fracture, whereas liquid CO2 create nuclear turbulence to into a fracture. Because of the hazardness of the liquid CO2 pumping, all personnel in the vicinity must be equipped with the hearing protection, because when the fast change from the liquid to gas, when pumps are cooled down or lines are emptied, it's extremely noisy. And where we can use the liquid CO2 fracturing in a low permeability in a dry gas reservoir where leak-up is to minimize to avoid the relative permeability damage effect. Oil wells do not respond as favorable for CO2 fracture treatment compared to gas wells. So oil wells, forget about it in a liquid CO2 fracturing wells. Because oil wells require a wider Proppant back and a fracture widths generated by liquid CO2 are narrower, and those that which can produce with conventional frac fluids. These are the schematic of the fracturing fluid and applications. You can find that the Slickwater application, low frictions, low viscosity, a low residue, less damaging, low proppant transporting capability. Okay, remind it for myself or for yourself. A linear gel application, mild friction, pressure, adjustable viscosity, high residue, because we can put, transfer the gel into more or lower. And high residual, more damaging, cross-linked application, high friction, high viscosity, excellent Proppant transport capability, high residual, and more damaging because braking doesn't perform good. If the breaker additive do its jobs better, will be give a cross-linked gel application better and energy side fluid applications like as a carbon dioxide, nitrogen, water sensitive for the water sensitive formation depleted under pressure wells, low permeable gas formation, high Proppant transport capability. These are the difference between the difference of in a fracturing fluid system applications. Additives, as its name comes, additives are material to use produce a specific effect independent of fluid type. Now, you know, additive as like as a medicine for the fracture fluid. When we use a water-based, okay, clay stabilizer should be used. Okay, clay stabilizer is a medicine for our fracture fluid to inject it into a well. We have more additive in hydraulic fracturing, but I want to explain some of them additive that are important for you, as like as a gelling agent, friction, breaker, crosslinker, clay controller, breakers, scale inhibitor, corrosion inhibitor, bactericides, oxygen, surfactant, foam agent, acid, anti-sludging. Anti-sludge for the oil that can use emulsifier, fluid loss agents, and resin activator. For example, buffer. A common buffer agent are used to control the pH for the specific cross-linking and cross-link times. For example, buffer for in acidizing, we use it for keep the pH around 4 to 5, because we don't want to precipitate the iron control. Okay, so we use the buffer. In a hydraulic fracturing, we use a buffer to control the pH for a specific crosslinker and crosslink times. pH adjusting chemical or aqueous fracturing fluid to maintain desired commonly buffer as like a sodium carbonate, sodium hydroxide, and monosodium phosphate. Another one is bactericides. Every time when most water used to prepare fracturing gels contain bacteria. It's because it's not a drill. Every time a drill water or pure water originating from the contamination of either source of rock in a storage time or location, and they produce enzyme to destroy the viscosity of the gel in the surface. So when we want to solve this problem, we should use some bactericides additive. Biocides should be used when the gel is premixed. Before the mixing, we should use it. Materials such as glutarate and chlorophene, bleach, or raising the pH over the 12 effectively control the bacteria. Breakers are told before that a thermal break of the polymer gel generally occurs in a well hotter than 225 Fahrenheit. So when we have a lower degree of Fahrenheit in our reservoir, we should put some breakers in a gel to break in the wellbore and give us a less residue of cross-linking gel. When creating lower temperature, vessel breaker should be added to fracture fluid. The viscosity of the gel and weight of the polymer should be significantly reduced to allow rapid cleanup the sand pack. Their use depend on the prevailing pH and temperature. Surfactant or mutual solvent are the famous additive that in acidizing or hydraulic fracturing we use. Surfactant or mutuals are added to fracturing fluid to reduce the surface tension of the fracturing fluid. But one thing, this is just for homogeneous the other additive into a fracturing fluid. Okay. Reduce the surface tension of the fracturing fluid to improve fluid recovery and compatibility between the fracture fluid and the formation matrix and formation fluids. The surfactant is molecular that locates at the interface and has the ability to alter the prevailing condition as like as a wettability or surface tensions. The surfactants give us or provide for us a water wetting, prevent emulsion, and lower surface tensions. Why prevent emulsion in acidizing is important for us? Because when acid goes to inside the deep well, we want in a shallow well, we don't want to emulsion the acid, and we use some surfactant as like a non-emulsifier surfactant to prevent emulsion and the acid reacted best with the formations. Clay stabilizers are more important and is important additive in a hydraulic fracture with water-based fluid because when the clay react with the water will be bigger, the volume will be bigger, and will be plug the pore through, and this is not good for the formation, permeability, and other things. So we use the clay stabilizers in our water-based fluid as like as a KCl, as like as the ammonium chloride, and like a calcium chloride, or some clay stabilizers. And one of the important additive is a fluid loss additive. The most common water-based fluid loss additive is found in ground silica floor with particles ranging from the 0.1 to 15 microns. Some additive or some things to help us to plug the face of fracture with little penetration into fracture into a formation matters is starches, diesel, gums, or resin, and also soaps. Soaps means like as a penetration agents. And another one is that guar polymer eventually control a leak off once a filter cake is established. So when we have a filter cake, we can use a guar polymer to control the leak off. Other additive that some additive that I want to explain is a viscosity stabilizer, because when we put the gelling agent, for example, into a well, we want to have a stable viscosity, because it's important for transporting Proppant. We can use some viscosity stabilizers added to fracture fluid to reduce the loss of the viscosity at high reservoir temperature. And the two most stabilizers are methanol and also the sodium thiosulfide. And another one is enzymes or protein molecules as organic catalysts that attach and degas the polymer at specific sites along the polymer backbone. One of the parameters that I told before is a fluid loss, and another one, fluid loss additive, and another thing, fluid leak-off. What is the fluid leak-off? As you can see here in a picture, when the fracture create filter cake in waiting zone and a reservoir, the fracture go inside to reservoir and give us the give us the leak of the fracture and give us the leak of fracturing fluid. The fluid loss behavior during a fracture has a large influence on fracture penetrations. Fluid loss depends on some parameter, depend on the fracture fluid, quantity of gelling agents, quantity of fluid loss additive, pressure differential across the fracture area, formation permeability and porosity, reservoir fluid viscosity and compressibility, and formation temperature. For the calculate the volume of the fluid leak-off, we can consider that our volume of injection will be equal with the volume of fracture and will be equal sum of the volume of fracture and volume of the leak-off into formations. Okay, the total rate and the volume of the fluid loss in a fracture described by the spark loss coefficients and the overall leak-off coefficient C and density. What is the spurt loss in for fluid loss? Spurt loss is a volume of the fracturing fluid loss instantaneously on initial exposure to newly created fracture wall per unit area. We can use and we can calculate the leak-off volume by quarter leak-off coefficients. You can see that the formula, it depends on the area of the leak-off and the quarter leak-off coefficient, and also a instantaneous fluid spurt loss. A spurt loss affect the rate and the volume of the fluid leak-off, and therefore the fracture growth. The value of the spurt loss can be obtained experimentally from the laboratory testings. The overall fluid leak-off coefficients represent a long-term average on a leak-off behavior over the duration of exposure. Again, always to tell you this part formula: volume of injection, volume of fracture, and volume of leak-off. So the volume of leak-off is so important for us, because when we want to calculate the volume of injections or efficiency of the pumping injection, we should know about the volume of leak-off. So how we can understand about the volume of leak-off with the spurt loss and with the coefficient, and also with this formula that we can give us the it can give us the volume of leak-off. So the fracturing fluid has many major variety conception, but two of them is more important for us: fluid loss, frictions, good transportability for the proppant, and also a good viscosity. So good viscosity helps for the good transportability for the proppant. Now, just I want to talk about the proppant. What is the proppant, and what is the purpose of the proppant? If you remember, in the first some slides, I told that when we inject the fluid, inject the pad, after the pad, we mix the pad with some element as a proppant to keep the fracture open. So these elements, the name is the proppant. So the proppant, we have a lot of type of the proppant, but some of the famous you can see in a picture, some the autobofraxan, some low density ceramic, so as the brown fraxan. But we have more type, some common types: sand, we have ceramic or intermediate strength or high strength, and another one is the resin proppant. If you can see in a picture, you can see the proppant embedment in a fracture. The proppant gather together, and now, okay, if the proppant go inside and fill the fracture, okay, now the permeability of the proppant is important for us, because if we do a fracture and we need this permeability to or conductivity to reservoir fluid comes to the wellbore and comes up. Okay, so if we see that one of the gel residue if remain in a Proppant embedment will be damaged and plug the formations and will be decrease the permeability. So our ideal Proppant properties is sustained high permeability, sufficient strength to withstand Proppant particle crushing under the increased rock, a uniform preferable spherical shape as this is spherical without any edges, a uniform, a resistant to fracturing fluid, formation fluid, acid, availability in a range of suitable sizes, availability in a large quantities, and at an acceptable cost. Low density is another ideal properties for the Proppant is the low density, preferably equal to that fracture to avoid the Proppant settling during transport in the fracture. You know, when the Proppant settling during the transport in the fracture or plug the perforations, it means or has expression that the Proppant screen out problem. Okay, so because of this, we should use some low density Proppant to prevent of occurring of the screen out Proppant screen. Size not only influences on permeability but also placement, since larger grains settle faster and breach more easily and can occur a screen out Proppant screening out. What is the difference between the frac sand and a VS and a Proppant? Frac sand is a natural sandstone, siltstone, with a high purity, very round grains quartz sandstone with a durable and crush resistant material. An alternative product is a Proppant that with ceramic bits made from the sintered bauxite or a small metal bits made from the aluminum. But both of them, the target of both of them is to keep the fracture open and provide the permeable pathway. So we should use a same size Proppant in a fracturing. It's good for us, and it's not advised. What is the sentence that I want to tell you? Please don't use a lot of size of the Proppant in a fracturing jobs. It's not good. It is not a good result for the operations. Common Proppants, as I told before, sand, intermediate stress Proppant, as a ceramic material, high stress Proppant, as a sintered bauxite. All of these Proppant can be coated with resin and be resin till that RCPS, resin-coated Proppant. Sometimes you will be comfort about this mesh scale. This mesh scale, the first number, it's a number called introduce us that can pass through by this number of mesh, and the second number will be filtered by this second number. So if you see now, what is some definition for the sand, intermediate and high strength and resin-coated Proppant? For what is the sand? We can use some famous sand, Ottawa sand and Bradley type sand. For example, not for Iran, we use the Ottawa sand or Bradley type sand. We use a sand like this size, okay? Just this is important for us. Ottawa sand usually 20 to 12, 12 to 20 or 20 to 40. Another one, intermediate, and another thing for the pressure closure, the sand is about smaller than the 6,000 psi. And another common propant is the intermediate stress propant. Stress of this propant is much closer to that the sinter bauxite, and the peak closure is about smaller than the 10,000 psi. Also called the intermediate density propant, and in a market can or trade we carbonate, naphthalate, and interprop can say. Another common propant is a high stress propant, like as a glass pits, and a peak and a pressure closure for the highest stress propant is between the 10,000 to 15,000 psi. Some trades name of high stress propant are Sinterprop, Carbo HSP, Sinterball, and Carboprop. Another one, as a resin-coated propant or RCPS, is used for the following main objective: to provide with the pure coating, increase strength of the propant. Okay, because we don't want to inject the propant with the fluid into a fracture and in a compressive strength crush the propant. So we use some resin-coated propant to give us the good strength and don't crush it, and doesn't crush in a compressive strength. And in other things, to prevent the back production of propant, I will explain it later. Common propant we have three type of the RCP resin-coated propant. It's a pure cured or tempered. Another one is curable, and another one is partially cured or stress bonding propant. Just keep in your mind every time we cannot use RCP with the VES fluid and also with the crosslinker, because sometimes the crosslinker additive reaction with the resin and will be damage our operations. So a propant carrying fractionated fluid is a complex mixture of several additives. Many of these additives can react with the resin coating of RCP, resulting in a reduced strength and a poor frac fluid performance, like as a Crosslinkers, breaker or oxidizer, and another polymers and bactericiders and another. Now, pre-cured or tempered, these are totally cured and have fully reacted. Traditionally, the function of the resin of pre-cured RCP is not much to glue the grains together, but to improve the strength and crush resistance of the propant. Another one is curable RCP. This RCP is coated with a curable resin that only needs to increase in temperature in order to cure. And a partially cured or a stress bonding RCP, the stress bonding RCP needs an increase in both temperature and pressure to form a consolidated propant batch. Partially cured RCP is most commonly applied type of resin-coated propant at present. So partially cured RCP is the most applied type resin-coated RCP. This is if it stand smaller than the 6,000 psi stresses, intermediate smaller than the 10,000 psi, high stresses 10,000 between to 15,000, and resin coated it's about 8 to 10,000 psi, and maybe lower and maybe approximate more. And this is the pyramid of the Proppant, and you can see that when we have a low conductivity, we have a sand, a medium conductivity, resin-coated sand, and high conductivity, we have a ceramic, because the ceramic has a sulfurity and roundness good. And as if you remember about the porosity in university, if you have a cubic type, we have about the 48% of the porosity, and if you have a rhombohedral, you have about the 26% of porosity. So these are a parameter for settling of Proppant together and gather together and give us the good permeability and conductivity. And if you see that when our size will be greater, our strength of our strength will be increased. One of the tests that we use in a field is sieve sizes and sieve analysis. What is the sieve analysis? If you remember, I told before, the second mesh number is that a Proppant can throw out, but the first one. But the second, the Proppant cannot throw out, cannot go inside. So the testing of Proppant size distribution is a quality control procedure done through a sieve analysis to obtain the particle size distribution of solid material while determining the amount of powder retained on a serious sieve with different size apertures. So I told before about the sulfurity. If you see that, this is it's has a good roundness, good sulfurity, and definition for the Proppant shape consists of two descriptions: sulfurity and roundness. Sulfurity is a measure of the degree to which Proppant particles approximate the shape of the sulfur, which is independent of its size. Yes, because the sulfurity is not dependent on the sizes. And the roundness is the measure of sharpness of a Proppant particle edges, corners, and smoothness. When our Proppant has edges, it's not okay. Maybe some edges get together and collide the way, and it's not good for us. When our sulfurity and roundness is good, so our result will be better. I told about the Proppant back productions. Proppant back production from hydraulic fracturing is one of the major operational problems to industry. Consider about the up to 25 to 30% considerable amount of Proppant can produce back to pre-created fracture. Proppant back production is the cause of the operational problem, especially in the offshore environment, because it can lead to hazardous situation to the erosion of pipelines and surface equipment for the adequate and costly disposal of the produced Proppant is required. Proppant, how we can identify the Proppant back production when we have a high rent Proppant production during the well cleanup. Another one, persistent Proppant back production at a lower rate without affecting the well productivity. So again, high rate Proppant production during well cleanup, and another one, a persistent Proppant back production at a lower rate without affecting the well productivity. Continuous Proppant production can be controlled by can be a stop of controlling the by producing the well unrestricted choke, but it's not good because the washout choke will be occur. From the full SNL laboratory experiment, it has been observed that Proppant back production tend to increase with increasing fracturing widths of over 1 centimeter widths. How we can prevent of the back production prevention? We can use the partial curable resin-coated, partial curable, another use of RCPs. It takes means the partial curable resin, and bringing back the well in order to reduce the amount of Proppant production on operation acceptable, installing a screen in a wellbore, injecting a resin to consolidate the Proppant back, use of RCPs, addition of mechanic additive to the Proppant as a fiber plastic strips, because again it gather, but it remains there's some pores road between us and the flowing coating of the Proppant with a liquid that makes the Proppant surface sticky and increase the surface frictions. Now you can see that fracturing fluid cross-link gel without the Proppant. With the Proppant, it will be this shape, will be this photo fracture fluid slurry. You can see the viscosity, you can see that the concentration of the Proppant, you can see all parameter just with the touch it, the gel. Another example, another sample is linear gel with the Proppant. If you see that this Proppant settling in a linear gel, but in a cross-linking gel with Proppant, it's a homogeneous and fracture flowing slurry. Again, if you see that, like homogeneous. So, Nikhil, now we can 5 minutes break. And again, we do a designing procedure and fracture equipment. Introduce a fracture equipment. This is the quiz too. If anybody wants to answer, please write it in a comment box. Thank you. For a 5 minutes break. Interpretation conditions. Expensive, operational to handle, not environmental friendly, water-based, safe, available, economical, and damaging to clays. Which chemicals are basically chemical purified form of the natural guar gums is the hydroxypropyl guar and carboxymethyl hydroxypropyl CmHPG and HPG. What is the common type of the emulsified acid? It's a polyemulsion that is 67% hydrocarbon interval phase, internal phase, and this 33% viscosified brine external phase. And what concentration of Proppant is not advisable in a foam is the greater than the 4 ppg. What are the advantages of the using CO2 in fracturing? The CO2 flow has advantage eliminating formation damage and rapid cleanup with no residue left of Proppant back. And what are some clay stabilizers like as a KCl, calcium chloride, and ammonium chloride? Another one, what is the sport loss? The sport loss is the volume of fracturing fluid loss instantaneously on initial exposure to newly created fracture wall per unit area. What are the common types of the RCP? Pure cured or tempered, curable or partially cured or stress bonding. And how can we identify the Proppant back production? We can with a high rate Proppant production during well cleanup and persistent Proppant back production at a lower rate without affecting the well productivity. Thank you, Selim, for your cooperation. And now we want to start about the hydraulic fracturing equipment layout. And after that, the design procedure. And at the last, we just show you about the Gopher software basic workflow. In a hydraulic fracturing equipment layout, we need some storage tanks, Proppant blender, pump tracks, monitoring control. If you see that, we should arrange all pump tracks and all of them as like as it is. But it depends of your well situations. Well situations, you see that data monitoring, frac spons, wellhead, frac blender, sand storage unit, chemical storage, and frac tanks, simulation frac tanks, and gel-slurry transporters. And you can see here on a well, we have some we should some manifold, we should some have high pressure lines for the 10 to 15,000 psi work pressure. We need a one unit or computer unit that we observe the pressure during the operation, also after the shutting time. And other things, this is the photo for the year of the 1960. And it's an old picture about the fracture acidizing. Some field engineer rule of thumb, how much horsepower we need to fracturing, which we can use it with the pressure and a dirty rate. Dirty rate, it means for the slurry rate for the PLF stages, because we should need a more rate because of the Proppant settle, because the Proppant should go inside the fracture and keep the fracture open. How we can find the dirty rate with the clean rate, multiply to a specific volume of sand, cross to prop concentration plus to 1. You can find the dirty rate and you can find the clean rate with this formula. This is a rule of some of the rule of thumb that you can, field engineer should know about this formula to calculate the horsepower of the how much the horsepower we need to and how many pump tracks need to or frac pumps need to pumping, find dirty. Another, find a dirty volume, how we can find the dirty volume, find the clean volume, find the slurry density. And these 6 parameters is important for the field engineer can calculate on a field, in a field. So now we reach to hydraulic fracturing design procedure. In hydraulic fracturing design procedure, first of all, we should find a good fracturing fluid. After that, we should find a good Proppant. After that, we should find a breakdown pressure and also a maximum allowable treatment pressure. Number 4, we should know and we should find the fracture propagation model, and another a treatment size volume, a fracture length and Proppant concentration, and another a Proppant, a perform forecast and NPV analysis, because we should want to check that if we do hydraulic fracturing, the cost is good for us or no, because sometimes the cost of hydraulic fracturing is more than the price of the production well, oil production in a well. So we eliminate the hydraulic fracturing and go to find another way for the simulation the well. So at first, the selection of the fracturing fluid, 2 major variables is important for us: fluid loss and fluid viscosity. Fluid loss characterized by fluid loss coefficient and spread loss, and that I explained before. The fluid viscosity that affects the transporting, suspending, and deposition of Proppant, as well as a backflowing treatment and other consideration. Yeah. We should check that compatible with the reserve fluid and also with the rock as a water. Do we and can we use a water-based fluid in a sandstone with a more clay element? No. So we choose another additive and also some parameter. Select a Proppant as you remember, I told before about the sand strength, pressure closure strength about the sand, high strength, intermediate strength, high strength, and pure and resin coated. And so we can choose a Proppant basis on the in-situ stresses conditions. Major concerns is compressive stresses that affect the stress of Proppant permeability. For vertical fracture, the compressive stress of the Proppant should be greater than the effective horizontal stress. In general, bigger Proppant yield better permeability, but Proppant size must be checked against Proppant admittance, create perforations and inside the fracture. If you see this curve, it's about for the closure stress and the permeability. If the closure stresses will be more, our permeability will be decreased. Another important things that we should know about the Proppant. Proppant is about the Proppant concentration. Proppant concentration refers to amount of Proppant added to crosslink gel, your clean fluid, to form a required fracturing slurry dirty fluid. Okay, it means that in ppg or pound per gallon. Proppant concentration in fracture fluid is designed to be ramped up, starting with lower concentration and then increasing during the pumping system to avoid Proppant screen out problem. So what is the screen out problem? A screen out is a condition that occurs when the solid Proppant carries out in the fracture treatment fluid, creates a breach across the perforations or a similar restriction flow areas. This results in a sudden and significant restriction to fluid flow that cause a rapid rise in a pump pressure. So ramp stopped. The Proppant concentration consideration is more important for us because we should ramp up gradually. During hydraulic fracturing, different Proppant concentration are pumped and gradually increase based on the initial frac design schedule and pressure response. If you see that some concentration of Proppant that injected into fracture, for the first one 1 ppg, and for the second one 1, 2, 3, and for the last one 5 to, and if you see that the ramped up the concentration of Proppant. Another one that we want to know we should know about the maximum treatment pressure. How we can calculate the maximum treatment pressure? It depends of the hydrostatic pressure, it depends of the friction pressure, it depends of the breakdown pressure. Okay, how we can calculate the breakdown pressure depend on the in-situ stresses that explained in first slides, primary slides. So with this formula, we can find the maximum treatment pressure, and with this formula depend on density, injection rate, fluid viscosity, and the tubing diameter and tubing length, we can find the friction pressure. Another one, a selection of fracture model or propagation geometry fracture model. Fracture propagation model is selected for the formation characteristics and pressure behavior on the basis of the in-situ and laboratory test. Modeling with a planar 3D model can be time consuming, yes, because we don't have any accurate data to put it in our software and give them a best result. This is not. And another thing I want to tell you, no software till now cannot give us accurate simulations. Every time your procedure, your schedule is okay, but the software will show you about the 100-meter fracture length, but it's not okay. It's just optimal and just the optimum shape of the fracture, nothing more. And the result from the 2D model can be simplistic, and however 2D models are still attractive, because now if you see the formula and if you see the that parameter are available, that we can put it in a formula and give us some important parameter that we want to analyze, like a fracture width or fracture width. And another one, PC3 model provides a compromise and are most often used in the industry. Select treatment size and volume. Treatment size is primarily defined by the fracture length and also a width and also a height, because we want to calculate the volume. Fluid and proppant volume are controlled by fracture length, injection rate, and a leak of properties. A general statement: the greater the prop fracture length and the greater the proppant volume, the greater the production rate of the fracture wells. The optimum scale of treatment should be ideally determined based on the maximum NPV. NPV I will explain in next slides. A production forecast and an NPV analysis. So we want to do a fracture jobs. So we calculate about the cost of the hydraulic fracturing and about the well production prices in the future for n years. And also we calculate and we find the number and we find the quantity that give find a quantity that give us is it okay to do a fracturing jobs or not. So that one, a formula that we want to predict the annual cumulative production of fracture well and unfractured well. How much the production will be, how much the production will be increased. And what are the costs of in NPV of hydraulic fracturing project? The costs include of expensive for fracturing fluid, for pumping, fixed costs for the treatment jobs, for trucks, for loading, for personnel, for every parameter that can be included in the that we include in a cost of hydraulic fracturing. Design treatment size using the KGD fracturing model, because our fracture area defined by two fracture half length and fracture height. If defined by the gamma, we can consider the PKM model. This is simple. This is a simple formula that you can refer to every book that see that this formula, this sample, and this example. But I do it for myself and do it in my Excel sheet file, and that do it also with the KGD model and also with the PKM model, and then give us my result, and that I can see and that I can compare it with myself. Because of this one that I told before, that if you want to be an engineer or anything, at first when you comfort with any formula, please put it in your Excel file and make your own software for your jobs. So, assuming a fracture half-life and injection rates, if we want, so the fracture half-life is important for us. The injection rate is important for us. And another thing is the volume of injection, how we can calculate the volume of injection, how we can calculate the volume of the frag, and how we can calculate the volume of leak-off. When we want to know if we want to calculate the volume of injection, because when we have suppose the rate of the injection and the time, we can find the volume of injection. After volume of injection, we can find the volume of frag with the fracture area and the fracture width. We can find the fracture leak-off volume. If you see that, if you remember about the formula, we can find it with this formula, but depend on the time. Because of this time, we should iterate a numerical procedure that I will explain in the next slides. And another thing that's important for us about this one is the fluid efficiency, eta. Eta means the ratio of the volume of frag to volume of the injections. So, and another one, when we want to find the volume of the pad that we want to inject, that it is depend of the volume of injection and the fluid efficiency. So if the fluid efficiency show us and increase it to 1 and indicate high proficiency of the use of fracturing fluid to propagate fracture, and to 0 indicates significant leak-off. If we have a leak-off, our fracture propagation may be not good. Another one, if you remember that I told you before, if because of the time, because first of all, we should find the time of the pumping, we should do a numerical iteration procedure with this one. Okay, when we have a volume of injection, we have the volume of fracture, we want the volume of the leak-off. Okay, volume of leak-off depend of the time. So in a time, we should find this KL. It's a multiplier. It's a parameter that we should guess at first and check it with the correct and incorrect. Check with the correctness. Check it. Is it okay or not? So after that, if it is okay, go and go another step and do and find the volume of leak-off, and another find the Proppant, and another things. Another is generate Proppant concentration schedule using. If you see that it depends of the time of the pumping of the pad, time of the injection, time of so the concentration using a schedule is depend of the time. The Proppant concentration in pound per gallon ppg can show. After we find the Proppant, we can find the product fracture width at last. How much the width of our fracture. So this is a example that we have a Poisson thickness, Young modulus, Poisson ratio, fluid viscosity, leak-off coefficient CT, Proppant density, Proppant porosity, fracture half-life, fracture height, fracture injection, fluid injection rate, and final Proppant concentrations. So we can find it. First of all, we should find the fracture width by KGD model. So when we find the fracture width by kg, the average fracture width by kg model, after that we find the fracture area, fluid volume based on the volume balances because of the time of the pumping, because of the rate of the pumping, and assuming, first of all, if you remember, we want to iteration, numerical iteration procedure. First of all, if you want to KGD model, you can assume that every time a KL between the 1.2 to 1.7, it's every time will be give us the result, but in a refer book we give us a bit. Suppose that 1.5, and with a 1.5 we can calculate the time 37 minutes. So we with this time we can check the KL value. If the KL value near to our supposed value, okay, now procedure is correct, and going to another part. So we find the volume of injection, we find the volume of the fracture, can be find the pad volume with this formula. If you see that the volume of pad and volume of injection, and with this formula, it's just for the and the concentrations. You can find the concentration if you in these slides we find the time 35 minutes, and here when we put a 35 minutes, we see that 35 minutes and give a slurry concentration is about the 3, and this is a proppant mixing schedule that you can find, and that you can put a time in it, and every time change it, that you can find the proppant schedule mixing. And proppant weight requirement, when you have the volume of injection and volume of pad, you can find the and the specific gravity of the proppant. You can find the mass of the proppant, and after when you know about the mass of the proppant, you can calculate the force the ratio of force to area that give us the gradient. After the gradient, we can find the width of the fracture. This is just about the we find the 0.04 inches, and with my Excel sheet, now you can find it with my Excel sheet. In my Excel sheet, but with KGD, our prop fracture width will be about 0.04442, because maybe some mistakes in our reference book. And another, if we want to do it with the PKN model, our prop fracture will be prop fracture width will be about 0.0415. And another sample, you can do it for yourself. With supposing this parameter, and do it for yourself, do it for your Excel file, and with this formula that I'll give you in a file and in a video that you can see in a YouTube. With this formula, our PKM model, with our PKM model and the average width, you can see that our prop fracture width about the 0.05.0, and with the KGD model, it's about this time. And these are the real main treatment schedule list. If you see that, first of all, we pump the pad, and after that we pump the slurry, and after that slurry we pumping the flush, and after that shutting, and after that we do a cleanup jobs. After cleanup jobs, this is again another schedule of pumping, because maybe if you you are a student and you don't see any real plan jobs, just every time you say that this formula is all parameter that you need for the designing. No, the designing plan is designing plan has more parameter for itself, has more rule for itself and something like this. And now this is a real main treatment schedule list for the first time freshwater water plant, the silver steam. This is the name of the one of the slurry that in the market, one of slurry pad, and after that the flush. And in this one we didn't see any shutting time, because this is a mistake, because they should put the shutting time, and also a cleanup, because in the procedure we should have all parameter. And when the clients ask you to give him the schedule list, they see all parameter, they calculate the cost for itself, for time and anything. And another, this is the real main treatment chart. If you remember that, if for the hydraulic fracturing jobs, for the first time prior to hydraulic fracturing, we should do a Mini-frac jobs, and after that we should do a main frac jobs. Why we do a Mini-frac jobs? If you remember, we can find the fracture initiation pressure, fracture propagation, and also the minimum effective horizontal stresses and other parameters. One thing that I was just a small fracturing jobs for low permeability reservoir is okay, but sometimes when our oil production is when our production enhancement in us is our primary goal, we do another fracturing jobs. The name is skin frac jobs. This one, this objective for bypassing formation damages, controlling sand production and sand consolidation, reducing fine migration and asphalting wax production, reducing water coning, improve communication between the sand-shell laminated reservoir and the wellbore, and other things. When the technique were mainly applied for bypassing formation damage, is frequently called skin frac. When applied for sand control reason, it is also known as a frac pack. A skin frac is a small propped hydraulic fracturing created with a limited volume of 600 barrel maximum of highly viscous fracturing fluid and some 10,000 to 100,000 pounds of Proppant, and using a forced tip screen out followed by fracturing packing or ballooning stage. And what is the ballooning stage? The ballooning stage, when pumps are turned off, stopping circulation, the fluid density is reduced to the mad width, which is not enough to hold the fracture open. The last circulation fluid is pushed out of the formation as the fracture closes. So we reach to go for software, and I explain rapidly about this software, because this software is like as another software in a market, has its policy, has its data entry. For each software that we about the fracturing, we in a fracturing market, I told before that no software now in a market is reliable, but Gopher now is reliable than another one. That now in a marketing for Gopher, we can find a well construction, petrophysics and geomechanic, and DFIT analysis, optimization, completion optimization, and a completion design and 3D simulations, production forecasting, like as MPV analysis, and about the decline curve and the ray tracing production analysis. The Gopher, which stands for Grid-Oriented Hydraulic Fracture Extension Propagate, is a planar 3D geometry fracture simulator with a fully coupled, fully fluid solid transport simulator. Gopher was developed by Dr. Bob Barry of Body Association in association with STEAMLab, a division of Core Laboratories. Two important parameters in a Gopher software is Gopher complete stress equation defined by this parameter, and as like as this one, and you can find it here. Gopher complete stresses about the Poisson ratio over radiant pressure, vertical bias for something. For elastic constant, for elastic is about the 0.65 to 0.72, and about with the original horizontal tectonic stresses, as all another simulator for the fracturing or acidizing. One of the steps is defining the well and data. Another one define the reservoir parameter, define the fracturing fluid, define the proppant, assuming proppant schedule, assuming pumping schedule, run model. After running model, you can see the simulator. The simulator will work or perform with that formula, and those formula that, if you remember, I told you before, with the depending on the time, because with the second time or with a minute time we will give us, and we should consider all parameter. And this is the schematic of the Gopher software. That for the Gopher, this is the icon of this Gopher software. You can create a project. You can choose you find the oil field or metric or SI you want to do your jobs. After that, you can load survey, or as the steam Pore or frac Pore, you can load LIS or CSV file that put a survey in it, and intertreatment survey in it, because if you want to put a survey with a TVT or MD, MD will be time consuming and will take a long time. After that, you can see you should put some reservoir data in it, and about the TVD pore pressure, about the water saturation, oil saturation, about, and you can find the logging data, and you put some logging data about the LAS file. And these are you can here you can find that about the logging processes, and you can see the total stresses, the color of total stresses. Each color has identified forget the name in English. You can find about a limit in a stress about maybe 1 to 1,000, 2,000, or 3,000 to 4,000. You can see in the software another design tab. In design tab, this software as another software, but that remain that exists in a market that didn't design for you. Just you should put your schedule, and with that schedule give you simulations. And another one select option This is if you want to do a real time, or if you want to design a schedule, you put your pumping schedule, for example, for the first time for the pad stages, put your 20 barrel per minute, and after that with constant rate or anything, you change the rate. If you change this rate, you can find the result after every time. You can find the result at the last report. You can find the fluid Proppant database in this software. Some fluid with some percent of KCl or anything, or acid or VS or anything that can include in a fluid. You can find it, or you can define it in a software. And also for the Proppant, after that you find it and define it for the pad stages. For the slurry stages, you can find run engines or run simulators in software. Tell that run engine. And in our simulation, if you see that, you can see some parameters like a bottom hole pressure, well pressure, injection pressure, bottom hole Proppant concentration at surface, Proppant concentration, because you put some data in it before you doing the job, and he calculated it with the parameter with that formula, depend on the time. Depend on the time, and again, every stresses has a specific color. Here you can see the result of Proppant concentration with the depths and with the vertical stresses defining. Here you can see that about the total stresses, about the total stresses with the TVD. And also here the engine, you can find some parameter I told for bottom hole, pipe fractions, fluid losses storage, all parameter. If you see in a picture, you can find all parameter with special color with this line. And run production model with the analysis, with about the DFIT analysis, view production output. You can see a production and generating report that you can find the report in a Word file, and or LAS report. After that, you can give it to your client. And this is my references that you can see. Thank you to all guys. And thank you for your attention, and best regards. And I wish that this webinar or workshops is good for you, and just a little give you a knowledge about the hydraulic factory. Thank you.
So thank you so much,